So a bit of a brief overview. This is the main core system, so the fuel will sit in here, be producing all the heat, and then we'll be utilising that heat, bringing it out of the system here to these two areas, and these are the conversion units. That's going to take that thermal energy and produce electrical energy that we can use on the moon. So a bit of a...
I'm at the Maintenance, Repair and Overhaul, or MRO, facility in Derby. This is just one of the locations in our global network where our engines come to be serviced.
What is the timeline?
So the objective for the microreactor is to have the first of a kind produced by 2028, with a view that for 2030 it'll be ready for launch. So that's in line with various programs that, for example, NASA have with our...
How did a British engine become Sweden's ultimate weapon for Arctic dominance? While the world looked elsewhere, Swedish engineers pushed the Rolls-Royce Orpheus to a blistering Mach 2, securing total tactical independence. This is the engineering masterclass on how sovereign propulsion technology keeps Sweden ahead of escalating threats in 2026. The secret to the Draken's legendary performance isn't just the airframe, it's the radical afterburner integration that redefined jet propulsion. By customizing the Rolls-Royce Orpheus, Sweden achieved a level of data superiority and operational autonomy their rivals can't match. We're dissecting the specific engineering breakthroughs that power the High North's defense. Can a nation truly be sovereign if it doesn't own its engine data? Sweden answered this by transforming the Rolls-Royce Orpheus into a customized powerhouse, ensuring they never have to rely on outside help during a crisis. Discover how this unique engineering marriage created the tactical superiority required to face today's regional threats.
In 2026, the High North is no longer a quiet frontier. It has become one of NATO's most sensitive pressure zones. NATO launched Arctic Sentry in February 2026 to strengthen security in the Arctic and High North, and Sweden joined the effort with JAS-39 Gripen fire aircraft. But Sweden's advantage did not begin with NATO. It began with a different question. What happens when your main air bases are destroyed in the first strike? Sweden's answer was BAS-90, a dispersed airbase system designed to spread aircraft across roads, hidden strips, and remote operating points, instead of concentrating them on large, vulnerable bases. Saab describes this concept as a way to keep aircraft separated, harder to track, and harder to destroy all at once. That idea still defines Swedish air power. The modern Gripen reflects the same logic. Saab states that the Gripen C can operate from runway sections as small as 800 by 16 meters, including ordinary highways. But this doctrine created an engineering problem decades earlier. Sweden needed a fighter that could go supersonic, intercept threats fast, and still operate from short, rough wartime runways.
That challenge produced the Saab 35 Draken. Its double delta wing was not just a design choice, it was a survival solution. The inner wing supported high-speed flight, while the outer wing helped with lower-speed handling and short runway performance. But the wing alone was not enough. Sweden needed the right engine, powerful, compact, and adaptable. That is where Rolls-Royce entered the story. The Draken used the Rolls-Royce Avon, licensed built in Sweden by Volvo Flygmotor under the designation RM6. This was more than an engine deal. It became Sweden's blueprint. Take world-class foreign technology, modify it for Swedish doctrine, build it locally, then turn it into national air power independence. That formula shaped Draken, influenced Viggen, and still lives inside Gripen. So the engineering secret behind Sweden's tactical superiority is not just thrust, it is integration. Engine, airframe, runway, geography, maintenance, and national doctrine, all designed as one system. And in the High North of 2026, that old Swedish lesson feels more relevant than ever. The strongest air force is not the one with the biggest bases. It is the one that can keep fighting after the bases are gone.
To make the Draken work, Sweden needed more than a fast airframe. It needed an engine that could do three things at once: push a double delta fighter through the sound barrier, stay compact enough for a small interceptor, and still support Sweden's short runway war doctrine. That engine was not the Orpheus,
It was the Rolls-Royce Avon, transformed in Sweden into the RM6, and this was the real breakthrough. The Avon gave Sweden a proven turbojet core, but Sweden did not simply bolt it into the Draken and call it finished. Volvo Flygmotor adapted it into the RM6 series, pairing British engine architecture with Swedish afterburner development and local production. The Draken's later RM6C engine was based on the Avon 300 series and used Swedish-developed afterburners such as the EBK-67. This mattered because Mach 2 was not just about raw thrust. At high altitude, the air is thin. The engine must breathe efficiently. The intake must slow supersonic airflow before it reaches the compressor. The afterburner must add energy without destabilizing the flow. And the aircraft must remain controllable while climbing fast toward an incoming bomber threat.
That was the Cold War problem Sweden had to solve. The Draken's double delta wing handled the aerodynamic side. Its sharp inner wing supported high-speed flight, while the outer wing improved lower-speed handling and runway performance. But the RM6 and afterburner gave the aircraft its punch. When the afterburner lit, extra fuel was injected into the exhaust stream. The hot gas expanded violently through the nozzle. Thrust increased. The compact Swedish interceptor became a Mach 2 hunter. The Draken officially reached Mach 2 in testing on January 14, 1960, using a modified Rolls-Royce Avon engine under the Swedish RM6 designation. Visually, the physics looked simple. Air entered through the side intakes. It was compressed inside the turbojet. Fuel burned in the combustion chamber. The turbine extracted energy to keep the compressor alive. Then the afterburner turned the exhaust into a second combustion zone. But the real secret was balance. Too much airflow disruption, and the compressor could surge. Too little thrust, and the aircraft could not intercept at altitude. Too much weight, and Sweden's dispersed runway strategy would suffer. The RM6 solution sat in the narrow space between all three. That is why the Draken was not just a fast aircraft. It was a compact engineering answer to a national survival problem. A British engine core, a Swedish afterburner philosophy, a double delta airframe, and one clear goal: Mach 2 performance without sacrificing Sweden's ability to fight from the edge of the map.
Sweden's real advantage was never just building aircraft. It was controlling what happened inside them. The Rolls-Royce engine partnership helped Sweden build a deeper industrial habit. Do not treat foreign technology as a sealed box. Study it, adapt it, produce it locally, then connect it to Sweden's own combat doctrine. That mindset became a strategic shield. Because combat, the most dangerous weapon is not always a missile. It is information. Who sees first? Who shares first? Who jams first? Who decides first? This is where Sweden separated itself from ordinary buyers. Many air forces buy off-the-shelf aircraft. They receive a finished platform, fixed upgrade paths, limited access to mission systems, and dependence on foreign approval for deep modifications. Sweden chose a different route. It built an ecosystem where the aircraft, sensors, electronic warfare, weapons, and data links could be shaped around Swedish requirements. That matters because electronic warfare is not a bolt-on feature. It is part of the aircraft's nervous system. The Gripen E is built around advanced electronic warfare, ASAP radar, communication systems, real-time signal analysis, and network sensor fusion. Saab describes Gripen E as sharing information in real time to create tactical superiority and improve survivability in contested environments. This is not just about fighting harder, it is about controlling the data chain. A fighter that cannot control its mission data is not fully sovereign. A nation that cannot modify its own systems must wait for someone else to approve its next move. That is why Sweden's customization culture matters. It reduces dependency, it protects sensitive data, it allows local upgrades, it gives pilots systems designed around their own threat environment.
Saab has made this idea explicit in export discussions too. Interoperability is not only about NATO standards like Link 16, but also about national control of secure data and mission systems. This is the contrast. Off-the-shelf procurement gives speed. Sovereign customization gives control. And control is what survives the first cyber attack, the first electronic strike, and the first day of a high-intensity war. There is no public proof that Western fighter systems contain hidden hardware backdoors, so the real issue is not conspiracy. The real issue is access. Can you inspect? Can you modify? Can you integrate your own electronic warfare? Can you protect your own data? Can you upgrade without waiting for a foreign political decision? Sweden's answer has always been yes, as much as possible. That legacy now connects directly to the modern Baltic defense architecture. Gripen E acts as the fast-armed node. GlobalEye acts as the wide-area sensor and command node. GlobalEye is built as a multi-domain airborne early warning and control system, using active and passive sensors to detect and identify objects in the air, at sea, and over land. Saab describes it as a real-time command and control asset. Together, GlobalEye and Gripen E turn the battlespace into a shared digital picture. One aircraft sees, another stays silent, a third receives the track. The network decides faster than the opponent can react. That is Sweden's deeper engineering secret. Not just a powerful engine, not just a fast fighter, not just a radar in the sky, but a national system designed around one principle. The country that controls its technology controls its tactics, and the country that controls its data controls the fight.
In 2026, speed is no longer only measured in Mach numbers, it is measured in response time. A drone crosses the border, a radar contact appears near the Baltic, a submarine cable is threatened, a bomber track emerges from the Arctic warning chain. The question is no longer how fast can the aircraft fly, the question is how fast can the entire system react. This is where Sweden's old propulsion logic becomes modern again. The Draken was built for a Cold War emergency: launch fast, climb hard, intercept high. Its RM6 engine, a Swedish license-built version of the Rolls-Royce Avon, gave Sweden a compact turbojet platform that could support Mach 2 performance while fitting inside a rugged interceptor designed for dispersed wartime operations. The Draken reached Mach 2 in testing on January 14, 1960, using a modified Rolls-Royce Avon under the Swedish RM6 designation. But the real lesson was not just acceleration, it was readiness. A fighter that cannot start, service, refuel, rearm, and relaunch quickly is only powerful on paper. That is why Sweden's modern Gripen family still reflects the same philosophy. Saab states that the Gripen C can refuel and rearm in less than 10 minutes for air-to-air missions, while the Gripen E can be turned around in around 15 minutes with limited ground crew and equipment, even from dispersed and unprepared bases. That matters in the age of hybrid threats. Sweden is not only preparing for traditional air combat, it is also investing in air defense and anti-drone systems to protect critical infrastructure, including ports, railways, airports, and nuclear facilities, in response to the wider security environment created by Russia's war in Ukraine. So the engine is no longer just a source of thrust, it is part of a national reaction chain. Cold start, rapid launch, short runway, fast intercept, quick return, immediate rearm, back into the fight. In the Draken era, engineers relied on mechanical durability, pilot reports, test data, and scheduled maintenance. The machine had to be simple enough to survive wartime pressure, but powerful enough to reach the bomber stream before it crossed Swedish airspace. Today, that logic has evolved. Modern readiness depends on sensors, software, engine health monitoring, and predictive maintenance. Rolls-Royce describes digital twins as virtual engine models that help improve testing, maintenance, efficiency, and lifespan extension by analyzing real-time data patterns. This is the modern leap. The Draken told engineers what happened after a flight. Digital twins try to predict what could happen before the failure. In Arctic conditions, that difference is critical. Cold affects fuel behavior.
Ice affects air intakes. Temperature shifts stress metal. Long-distance patrols punish engines before combat even begins. A modern tactical asset cannot wait for something to break. It has to know what is weakening before the pilot takes off. That is where predictive analytics changes the battlefield. The historical Draken performance curve was about climb, thrust, drag, and acceleration toward intersection altitude. Public sources do not provide one clean open-source acceleration chart for every operational Draken variant, but the disclosed markers are clear. Mach 2 capability, high-altitude interception, RM6 Avon-based propulsion, and short runway design. Modern Swedish assets measure performance differently. Not only how fast did it climb, but also how healthy is the engine, how much life remains in the hot section, which component is trending toward failure. Can this aircraft launch again in 10 minutes? Can the fleet maintain 24/7 readiness across dispersed bases? That is the new propulsion battlefield. The Draken's RM6 gave Sweden the speed to intercept. Gripen's maintainability gives Sweden the tempo to respond. Digital monitoring gives modern forces the ability to stay ready before the crisis becomes visible. And that is the shift from Cold War propulsion to hybrid war readiness. Yesterday, the engine had to win the climb. Today, the engine has to win the clock. Because in the Baltic and the high north, the first advantage may not belong to the aircraft with the highest top speed. It may belong to the aircraft that is already warned, armed, diagnosed, and ready to move before the threat becomes public. The story begins with one British engine, the Rolls-Royce Avon, built under license in Sweden, adapted by Volvo Flygmotor, and reborn inside the Saab Draken as the RM6. But Sweden did not simply import thrust, it imported a foundation, then made it Swedish. That choice created a doctrine that lasted for decades. Do not depend blindly, do not buy passively, and do not fly systems you cannot sustain, modify, or understand. This is the real legacy of tactical independence. Sweden joined NATO on March 7, 2024, becoming the alliance's 32nd member. But NATO membership did not erase Sweden's defense identity. It changed the battlefield around Sweden, not the logic inside Swedish engineering. That balance is visible in propulsion. GKN Aerospace remains the OEM capability for the Gripen CD RM12 engine worldwide, and is building support capability for the RM16 engine that powers Gripen E. Engine sovereignty does not always mean designing every turbine blade from zero. It means controlling the life cycle, maintenance, upgrades, testing, data, readiness, and fleet availability. In 2026, this is no longer theory. GKN delivered the first upgraded RM12 engine to the Swedish Armed Forces under the Gripen CD Enhanced Performance Program, strengthening long-term performance and supportability. That is the modern Draken lesson. The RM6 gave Sweden speed. The RM12 and RM16 ecosystem give Sweden endurance, availability, and control. And in the Baltic region, control matters more than ever. Sweden is sharply increasing defense spending, with its 2026 military budget expected to reach 2.8% of GDP. New investments target air defense, anti-drone systems, and critical infrastructure protection. This is not just fighter versus fighter. It is sensor versus sensor, drone versus radar, missile versus air defense, and cyber pressure versus command networks. That is why Gripen E and GlobalEye matter together. Gripen E brings sensor fusion, silent networking, and tactical information sharing. GlobalEye provides real-time surveillance across air, sea, and land. One system detects, one system decides, one system strikes. And Sweden controls the architecture behind them. A mid-sized power cannot outspend every rival or build the largest air force. So it does something different. It masters the heart of the aircraft. Whoever controls the engine controls readiness. Whoever controls readiness controls tempo. And whoever controls tempo can shape the fight before the first missile is fired. That is the legacy of the Rolls-Royce breakthrough. A British engine became a Swedish doctrine. That doctrine became an industrial culture. And that culture now gives Sweden something larger than airframes: independent tactical influence inside a much larger alliance. In the Cold War, Sweden prepared to survive alone. In 2026, Sweden fights inside NATO. But the engineering principle remains unchanged. Never build an air force you cannot control. Never rely on power you cannot sustain. And never forget, the heart of the aircraft is also the heart of national strategy. Thanks for watching.